get started. So today I'm very excited to introduce our speaker, Haimin Hu. So Haimin is final year PhD candidate in ECE at Princeton. His research integrates dynamic game theory with control system safety and RL to enable trustworthy human-robots interactions. Previously, he got his master's degree in electrical engineering from UPenn and also BE from Shanghai Technical University. In last year, he was named as AGI pioneer by IGV and ACM. So I have the chance to talk to him a little bit. He gave me some preview about some very cool robot demo he's gonna show. So I'm very excited about these demos, and I think you're gonna be in the treat. So please welcome Haimin.
Thank you so much, Tammy. Thank you so much, everyone, for coming to my talk. So today I'm going to talk to you a little bit about my work on game-theoretic integration of safety and learning for human-centered robotics. So I think there's never been a more exciting time than today to work on robotics. And recently, we've seen a lot of exciting developments in this kind of intelligent systems. We've seen, for example, humanoid robots from Figure that can autonomously assemble parts 24/7. We have seen way more autonomous driving vehicles, which are capable of driving on sloping roads in San Francisco, dodging the heavy traffic and safely making unprotected left turns. And this is a mini-city setup we built at Princeton. You can see that the trucks here are coordinating with each other, taking turns to pass the roundabouts and intersections. And in the end, they were able to safely form a platoon on the highway of this mini-city setup. Well, everything just looked fine in this controlled lab environment. But let's imagine what could be happening if we're going to deploy this system in the real world settings. What if there are some humans around these trucks? Or what if one of the trucks is driven by human drivers, and therefore they may not coordinate well with other automated trucks? Or what if the road condition isn't that good? For example, there's ice on the road. Unfortunately, sometimes robots are surprisingly bad at reasoning and maintaining safety in this kind of human populated space. And I think a fully reliable robot is still a long way to go from, for example, this one, that it didn't realize it was not okay to stop in the middle of a busy highway and single-handedly causing a severe traffic pileup. So we need robots to safely interact with people, not only in this kind of controlled lab environment, but also in the wild real world that is fundamentally uncertain and unstructured. So we have a lot of elements to address there, like safety, people, and uncertainty. Question is, can we find a universal frameworks that allow us to address all these elements here? So in this talk, I will try to convince you that a useful tool we can use is dynamic game theory, which are games that evolve in time. So in this game, each agent will try to find the optimal way to complete their task at hand. For example, the truck here will want to find a minimum time pass to reach its destination. And as you can imagine, this optimization will subject to some constraints, like the vehicle dynamics or the requirement that we want each truck to stay within their lane. And most importantly, we want the robot to never ever hit the people. And it is this constraint that starts to complicate the problem, because now the outcome of this decision-making problem really depends on both the human and the robot's decision. And that's what makes this problem a game. And now, if the robot wants to safely operate around people, it needs to predict the human's future movements. And that's necessary because oftentimes people will not directly talk to the robot about where they're heading to. For example, today, I might want to come to JHU to give a seminar talk, or I might want to go home and sleep. So to remain cautious about that uncertainty, the robot can put a belief state over that human intent to maintain cautious. And that belief can be updated using some runtime learning algorithm like Bayesian inference or some more advanced theory of mind model, for example, like the ones that are developed by Haimin's group here. And this game framework is even more flexible in that you can add an additional adversarial player to model some uncertain elements in the environment, for example, the icy road condition. And finally, it is always possible to expand this game by adding more and more players. Well, this formulation may look reasonable, but despite all these research effort happening in the past few decades, this game here remains very challenging to solve. For example, the belief dynamics here are nesting the optimization and belief propagation, and that makes the game much more challenging to solve than a deterministic counterpart. And also, it's not trivial at all to come up with a non-conservative safe strategy, one that is more interesting than simply asking everyone to not move and stay there. And finally, we want to make sure that the computation here is efficient and scalable so that we can implement the controller in real time and on hardware systems. So in order to turn this game formulation into some practical algorithm that can be deployed on a hardware system, my work so far has integrated insights from machine learning, control theory, optimization, and game theory. And my key technical idea I'm going to show you today is that robots should plan strategically in the joint space of physical and information states so that they can actively ensure safety and reduce uncertainty about their human peers. So in today's talk, I want to focus on 3 key aspects of my work. First, I will talk more about how we can model human-robot interaction as a dynamic game. And then we will leverage a tool called safety filters to combine with this game formulation to make sure that such human-robot interaction is verifiably safe. Then I will show you how we can compute such a safety filter for high-dimensional robotics applications. And we will also look at multi-agent settings. There I will show you how we can exploit the problem structure of a dynamic game in order to optimize the team performance when robots need to collaborate with each other and collaborate with people to complete some task efficiently. So without further ado, let's look at the first part on safe human-robot interaction. So if we are going to deploy a robotic system in the real world, unlikely events, especially involving humans, are bound to happen all the time. For example, here, we have a person suddenly jumping out of nowhere in front of a vehicle. And here we have 2 people suddenly started a fight. So in these extremely challenging scenarios, how can robots guarantee safety despite these unexpected human behaviors? And more importantly, how can they do so in a way that minimally affects their performance? For example, here we want the truck to dodge the jaywalking or fallen humans by minimally deviating from that time optimal path in orange. And turns out that robots can do this in a systematic way and uses a supervisory control method called safety filters. So what is a safety filter? In this framework, we have a robot's performance-oriented task policy that proposes a candidate action in order to optimize the robot's performance. And at the same time, we have a safety filter that continuously monitors the system and intervene with their candidate action if possible. And this overriding rule can allow the robots to maintain safety without having to change its entire behavior, which is nice. And in our recent paper, we have proved that there's a universal safety filter theorem which says that for any safe control methods, if they satisfy 2 key properties, they will be able to ensure recursive safety. That means if you start safe, then you can guarantee that the robot remains safe for at least a future horizon. And this also allows us to understand a lot of existing safe control methods in a universal theoretic framework. And we can verify the safety guarantees we need in a constructive way. So with this nice theory at hand, we were excited to try out our safety filters on some of the robots from our industry collaborator. And this is a scaled autonomous driving setup we had at the Honda Research Institute in San Jose, California. And in this setup, we have a self-driving vehicle in the back and a human-driven vehicle in front. And both vehicles are constrained within the road limit. And the robot's target lane is the inner lane. And it's also tasked to overtake the human-driven vehicle if possible. So to do that overtaking maneuver, we equipped the robot with a game-theoretic overtaking policy, which is safeguarded by this safety filter that is synthesized based on Hamilton-Jacobi reachability. And the human in this case may or may not give way to the robot by changing its lane. And the robot needs to figure that human intent out at runtime. So now I will play 2 videos on the right to show you the robot's behavior under this safety filter. So in the first experiment, we can see that the robot's motion is very shaky because the safety filter got triggered a lot and it intervened with the normal driving quite harshly. And in the second experiment, you can see that the robot was very conservative and was simply unable to complete the overtaking maneuver. So our theory about safety filter was indeed correct, and the robot was able to maintain safety, but we don't really like this suboptimal behavior of the robots. And fundamentally, this is because the robot's task policy are ignoring 2 important factors about the human. First, because the task policy and safety filters are completely separate modules from each other, so the robot cannot predict these inefficient last-minute interventions that are caused by these unlikely human behaviors. And also the task policy didn't account for the robot's evolving uncertainty about the human. So the robot didn't know how to actively reduce that uncertainty in order to come up with a more informed plan. Like in this case, if the robot always thinks the human is equally possible to drive on both lanes, then there's simply no way the robot can ever find a feasible overtaking path. So our solution is conceptually simple and directly targets at these two issues. First, we will design a task policy that can predict costly safety intervention in the future. Then we will augment the robot state space with beliefs. So we can plan the robot's motion and account for how the robot's belief will evolve over time as a consequence of both the human and robot's decisions. So let's now look in detail how we can implement these two changes. First, we will plan the robot's motion with a joint state. Let's call it Z. And the joint state Z has both the human and robot's physical states, like their velocity and position, so we can reason the strategic interactions between these two parties. And also, the joint state has the robot's belief about human, like whether the human is willing to change lane and yield to the robot. And that joint state is evolved by a dynamical system, which also has both the physical component and the learning component, like Bayesian inference or some neural predictor. And a key aspect of this joint dynamics is the robot control now can actively affect the robot's belief state. In other words, robot can purposefully choose an action to probe the human in order to get more information and reduce uncertainty. And that is formalized by a theorem we proved, which shows that the robot's control can affect higher order moments of the robot's belief state. And this entails a nice control theoretic property called dual control effect from the 1960s. It shows that the robot's control can automatically trade off exploration and exploitation. Although this is a known result in the system ID or POMDP literature, we have really proved it for the first time in the game-theoretic settings. And we also show it as a useful property for human-robot interaction in particular, because nobody likes being probed by a robot all the time. And the robot should only interact with people to gather information to the extent that benefits with the robot's planning performance. So now that we know how to propagate the robot's belief state, we can optimize the robot's decision over a scenario tree. And that is defined by different realization of the human uncertainty. And this tree allows robots to predict some cost interventions that are triggered by different interaction modes between the human and robot. So the robot now can adjust its action from early on in order to avoid having to use these inefficient last-minute maneuvers. And we call this property filter awareness. And most importantly, when things comes down to assurance, because we always have the safety filter on top of this probabilistic reasoning, so we always have safety being guaranteed, even if that learning dynamics poorly represent the robot's uncertainty. So now let's check back and see if the robots can do better this time with these features implemented. And indeed, we see that the robots this time was able to complete the overtaking maneuver more smoothly. And we can compare it to an oracle planner, which knows the opponent's plan a priori. And you can notice how close these two trajectories can resemble each other. So far, we have only focused on the robot's task policy. But now let's also turn our attention to the robot's safety filter and rethink a little bit about its operational design domain, or ODD. So ODD is basically a set of safety or failure conditions that all stakeholders like users, manufacturers, and policymakers will agree on. And the core philosophy behind ODD-based safety is it will provide you with a clear-cut social contract. That means if you give me an ODD, I can design you a safety filter that guarantees strict safety. For example, one critical ODD element in human-robot interaction is the set of possible humans control actions. And it's possible that at some point, you might need to enlarge that human control set to cover some unlikely but safety-critical tail events. And if you design a safety filter based off of that enlarged ODD, the robot's behavior might be very conservative. So how should we do better in this case? Well, the idea is that just like the task policy, the robot's safety filter also needs to adapt to the evolving uncertainty about the human. So the robot can dynamically adjust its ODD to reduce the conservativeness during this safety filter process. So let's now see how we can design a belief-based safety filter based on this idea. So first, we'll partition the human control set with some hypothesis theta about the human. And that hypothesis could be modeling the human's semantic class, their intended destination, or their attention level, for example. And we can then use the robot's belief state to adjust this human control set. And here, each subset will be associated with a probability from the robot's up-to-date belief state. As usual, we can update the robot's belief using runtime learning algorithm. And we can set a small probability threshold. And if we find that the subset probability is below that threshold, we can remove it from the human control set. Yes. Over the theta space. And theta is describing whatever information that about human that is necessary for successfully carrying out the human-robot interaction task. So in the driving setting, for example, that theta can represent the human's possible locations, intended destinations, or for example, their attention level. So whatever information that is needed for the planning.
So it is very problem specific.
Yeah, I would say so. Yeah. Yeah. Also, it's part of your ODD design, actually. Yeah. Okay. So once the subset is removed from the human control set, it is only removed temporarily, because later on, we might find that that subset might regain some probability mass. So in that case, we will need to add it back. And this can nicely avoid the robot being overly optimistic. And that is the key property that differs our approach from some existing approach like contingency planning, which will actually discard all these low probability events once and for all. And that might cause the issue of robots ignoring some unlikely but safety critical events later on in the future. So with this formulation, we can now analyze the robot's robust safety by setting up a zero-sum dynamic game between the human and robot. And here the human is the attacker and robot is the defender. And mathematically, this will translate into a Hamilton-Jacobi reachability problem defined in a joint physical and belief space. And then we can use existing computational machinery to solve the HJ reachability for a safe control robot policy. And in terms of guarantees, our only assumption is called the inference hypothesis, which basically says that each time the robot's belief have to assign no less than that threshold probability to at least one hypothesis theta that is reflective about the robot's next move. And a simpler way to say that is we require the robot's runtime learning module to be accurate enough. And if that indeed holds, we can show that this belief space HJ reachability can indeed give you a valid safety filter. But of course, in practice, that inference hypothesis could be violated. And in order to investigate that issue, we have performed a quantitative study which shows that the belief space safety filter can still give you a much higher safe rate than these baselines that do not leverage the full belief information. And in terms of performance, when the robot is using the belief space safety filter, it can achieve a time efficiency that is almost comparable to these optimistic baselines. And this is true whether or not the human complied to the inference hypothesis or not. And on the other hand, if you only use a baseline that do not adapt to the uncertainty, then you will find that the robot was simply not able to complete most of the tasks in time. And you might notice that this is the well-known freezing robot problem. And right now we are working on using statistical tools like conformal prediction to calibrate the robot's runtime learning in order to have end-to-end probabilistic safety guarantee for the robot. So we have applied this belief space safety filter to some real-world autonomous driving examples from the Waymo Open Motion dataset. Here we use the motion transformer as the runtime learning module, and that was the state-of-the-art trajectory predictor used in traffic that can output multimodal prediction of the human vehicle's future trajectory along with their probabilities. And now I will play the video on the right, and you can see that the Eagle vehicle in orange was able to maintain safety despite that adversarial human who tried to block the robot and collide into the robot. And this is also the first result on multi-agent safety analysis that is done in close loop with generative AI models like a transformer. If the robot only used a safety filter that reasons in the physical space only, then the robot was very conservative and it went all the way to the road boundary and ended up leaving the road. And now we are working with Toyota Research Institute to apply this belief space safety filter to build an AI copilot for performance car racing. Here, the safety filter will try to activate align with the human decision, so the intervention is minimal. And you can see that it even works when the human's hands are off the wheel. So as a quick recap, I've introduced several design principles that can make robots safer and smarter around people. First, here we need a safety filter to guarantee the closed loop safety when the robot is deployed in a human populated space. And on top of that, we use a filter-aware game policy to make sure that the robot's task performance can account for these costly, inefficient interventions. And finally, and most importantly, we let the robot reason in the joint physical and belief space so the robot can maintain safety, but in a non-conservative way. So at this point, you might be asking, why don't we cast safety and performance as trade-off and tune that epsilon parameter to either get a better performance or a higher safe rate? Well, for this kind of, I call safety gambits, the robot is always risking a catastrophic safety failure, especially when there is an unlikely event happened. For example, here, the human-driven vehicle made a sudden right turn that is not predicted by the robot. And that resulted in a fatal crash, which took us several days to fix damaged motors on the vehicles. And in reality, this could mean life-threatening events for the passengers on both vehicles. Instead, we can augment this probabilistic approach with safety filter-based frameworks that I just talked about. And the idea is to be able to guarantee strict safety under a specified ODD. And to me, that is ultimately more accountable and more trustworthy. This essentially turns safety gambits into performance-oriented, into safety-assured performance tuning. So you can basically come up with different algorithms for runtime learning and filter awareness to fine-tune the robot's performance. But on top of that, we will always be able to guarantee safety under a specified ODD. So if there's only one key takeaway you can remember from my talk today, that will be safety and performance don't really have to be a trade-off for human-robot interaction. And it is possible that we can guarantee safety while minimally affect the robot's performance. Now with the safety filter-based framework, we know how to do it. Well, this is all great, but so far we haven't talked at all about the computation complexity behind these safety filter syntheses. And unfortunately, traditional safe control methods like HJ reachability analysis, because they rely on dynamic programming on a grid, which is ultimately affected by the curse of dimensionality. That means they do not scale beyond 7 dimensions. So how should we compute safety filters for all these fascinating but high-dimensional problems above that red line? So let's recall that a neural network is also a universal function approximator. So instead of using the grid representation, why don't we try learning a neural safety filter, which is much more scalable? And in particular, this idea has been extensively studied in the past 5 years, but mostly for single-agent safe control problem. But the theory and practice are still pretty much underexplored for learning safety filters in multi-agent case, especially for these zero-sum interactions that we just saw, which are necessary for reason robust safety for human-robot interaction. So this leads to the second part of my talk, where I will talk about how we can compute multi-agent safety filters at scale. More concretely speaking, I will show you how we can learn a best effort control strategy for this kind of robotic systems subject to adversarial disturbances. And I will be focusing on controller synthesis using deep reinforcement learning. And I will also be using game-theoretic tools so that this kind of multi-agent training can converge to a meaningful and useful solution. So my method builds on the so-called actor-critic reinforcement learning. And I will briefly introduce it so that we are all on the same page. First, we have a critic that minimizes the mean square Bellman error. Here, the state action value function Q can in fact approximate the same safety value function that is used by the belief space safety filter that we just saw. And then we have a controller player who will maximize that critic function. And finally, we have a disturbance player who will minimize the same critic function in order to jeopardize the system safety. And in this zero-sum setting, existing approach like robust adversarial reinforcement learning have been focused on using alternating optimization to do the training. This means that the controller player will learn its parameter by freezing the disturbance player's parameter, and vice versa for the disturbance learning. And the hope is that this kind of iterated optimization will eventually converge to something. But in practice, this kind of convergence is actually very difficult to achieve. And if you deploy a non-convergent policy on a robot, it is likely that the robot is going to be exploitable by some adversarial disturbance. And this ultimately will mean a lower safe rate for the robot. So in order to guarantee training time convergence for this kind of adversarial training setting, our key idea is to model the training process as a Stackelberg or leader-follower game. This essentially turns the problem into a tri-level nested optimization. Here, we let the disturbance player to declare its strategy the last, so it will have an instantaneous information advantage. And that matches our goal of reasoning safety in a robust sense. And more importantly, this formulation allows us to use a technique called finite timescale separation. There, the idea is to basically set a higher learning rate for the follower than for the leader. And with that, we can guarantee the training can converge to a local minimax equilibrium solution. And this is also the first two-player safety RL algorithm that is provably convergent. Again, why do we care about convergence here? Let's now see if a converged policy can actually help the robot become safer and more robust. Here we applied our algorithm, which is called Magix, to a safe locomotion task on a unitary go-to robot. And the state space of the robot is 36-dimensional, which is way beyond the 7D numerical tractability for edge dirigibility. And my colleague Dewey here is tugging the robot from the side and from multiple different angles. And the robot was able to resist up to 120 Newton pulling forces without falling over. And that force is almost equal to the robot's entire weight. Now, with a baseline policy trained with alternating optimization, you can see that the robot flipped over once that pulling force just exceeded 80 Newton. Now you might be wondering if this learned policy will ever overfit to a specific adversary. So to investigate that issue, we have trained multiple models with different random seeds for both Magix and for the baseline. And we let all these policies to play against each other, and we record their maximum and minimum rewards. And here you can see that the reward gap with the Stackelberg RL algorithm is much narrower than the gap with the baseline algorithm. That means that Stackelberg RL policies are much less exploitable. And that also means that they can much better handle the overfitting issue. So for today's talk, I've only focused on the convergence aspect of multi-agent safety. But that actually leaves us with some important question about how should we verify the safety of these kind of systems at runtime. And indeed, I've actually spent quite some time working on that. For example, I've designed one of the first algorithms to learn from scratch a control barrier function, which is another kind of very popular safety filters. I've also designed algorithms to verify that the learned barrier function is a valid one. I've also designed an optimization-based approach to verify the safety of dynamical system enclosed with a neural network controller. And that is actually a collaboration with Makia here. So in the interest of time, I will have to skip all the details here, and I will be happy to talk about these works offline. So far, we have always been focused on this kind of adversarial setting because we wanted to account for some unlikely human behaviors and reason about robust safety for human-robot interaction. But what if some coordinations among agents are possible? And that is often the case with our day-to-day driving, and it's also one assumption we are comfortable making for a lot of human-robot collaboration tasks, like robot-assisted surgery. So I wanted to switch gear a little bit now and talk about how robots can coordinate with each other and with people in a safe and efficient way. So it's quite surprising to me that even in some very well-coordinated settings, robots can still make serious mistakes. So here is an automated factory built by a company called Ocado in the United Kingdom. And in 2021, 3 of their robots collided with each other and ended up setting a big fire in the factory. And as a result, the company had to cancel thousands of orders, and their shares dropped 3% in the following day. So for this kind of multi-agent coordination scenario, we can usually identify 2 types of stakeholders: a regulator, like a traffic light, and a group of interacting agents. Here we assume the agents are self-interested and driven by their individual utility, like avoiding idle times and arriving at their destination as soon as possible. And the regulator will oversee the many agents to ensure their safety and maximize their collective efficiency. The question is how the regulator can balance this trade-off between optimizing social and individual performance. So we propose to formulate this multi-agent decision problem as a hierarchical Stackelberg or leader-follower game. Here we let the regulator dictate the agent's order of play, and then the agents will execute a game policy based on that order of play. So to solve that game, we use a quite popular distributed control algorithm called sequential trajectory planning. The rule is that a lower priority agent needs to give way and avoid collisions with higher priority agents. And that allows us to decompose the problem into smaller pieces, and that helps with the scaling. The remaining question is how should the regulator optimize over that order of play in order to maximize the aggregate performance? And the brute force approach, as you can imagine, is to exhaustively enumerate in that space of orderings. And we can record the social cost of each subgame and pick the best one. But if you do that, the computation complexity will blow up factorially. This means that you will spend about a week to solve one single problem instance involving 10 robots. And that is totally unacceptable. So to reduce that complexity, I designed an algorithm called branch and play. The key idea there is to use a search tree to speed up the computation process. And we construct that tree is by assigning only some partial ordering to players, and then these unassigned players will play along and ignore everyone else. For example, here we have a 4 UAV collision avoidance example, and that is the root node of the tree where nobody has been assigned an order. So you can see that the players basically penetrate through each other and go to their destinations. And because there's no safety penalty here, the social cost is pretty low, and we can use that as an optimistic lower bound estimate of the optimal cost. And then we can extend the tree by assigning order positions to more and more additional players. And our only requirement is called admissibility. This means that the social cost of a partial permutation should be a lower bound for a complete children permutation. And that is a fairly standard requirement for a lot of graph search-based algorithms like A*. And now we can use the cost of these leaf nodes to prune some branches in the tree. Yes?
Branching over what space?
Over the ordering space.
Algorithm space.
Ordering. So, for example, here we have 4 UAVs, right? So it follows a chain structure. So we have a leader, follower, and last follower. So you have different orderings that can be assigned to these 4 players. And one of the ordering will give you the best performance, and we want to find that one.
Are all the follows have the same order? Or
No. So it's one after another. It's a chain structure, but it's possible to combine some of the players, and then you will have a nested game where if you have 2 players have the same order, then these 2 players will play a Nash equivalent policy, but the others will play a stack overlap or leader follower structure. But yeah.
One last question.
Sure.
When you say ordering,
Yeah.
you're referring to the order in which you're optimizing the objectives of individuals' agents,
Mhm.
or perhaps some other meaning.
Yeah.
What is the semantics of ordering?
Yeah, so here we are looking at the Stackelberg dynamic game, which means that if you are a follower, then you will try to optimize your performance given the leader's strategy. So you are responding to your leader. And also additional rule here is if you are a follower, you need to avoid the leader, but the leader doesn't have to avoid the follower. So you are like decoupling the responsibility here.
So every follower has it.
Yes.
And every leader might be leading some other.
Yes. Yes. Yeah. Cool. So at this point, we can actually use the cost of some leaf nodes to prune some branches in the tree to speed up the computation. And the reason why we can do that is these underperforming non-leaf nodes like the one in the middle, because of admissibility, and we know that even if we keep extending that tree, their performance cannot further improve because of admissibility. So we can prune that branch out. And then you can keep exploring other part of the tree and prune some branches if possible to speed up the computation. And we actually proved that this branch and play process can indeed give you the socially optimal permutation without ever like accidentally pruning it away. And although the worst case complexity is still factorial, we find in practice that this upper bound is actually very rarely hit. So here's an application of branch and play to an air traffic control problem, which is surprisingly still a very hard problem. And we know that a tragic air collision happened in Washington, D.C. just a few weeks ago. So in this example, we have 8 aircrafts initially flying on collision courses. And the baseline we are comparing to here is called first come, first serve. That means if an aircraft first enters this air traffic control zone, which is this gray circle, they will be assigned a higher order of play. So I will play the video here, and you can see how the agents are interacting with each other. And we can see that with branch and play, which dynamically swapped ordering for the players, it can result in efficient trajectories pretty much for everybody. But in the baseline case, because these lower priority agents need to give way to higher priority agents, they need to even fly outside of the air traffic control zone and then loop back, which was very inefficient. And in particular, if we look at the numbers, branch and play can give you a 35% improvement in terms of time efficiency comparing to the baseline. And for the computation time, empirically, we find that branch and play can usually converge within a fraction of the second of the brute force approach. And in particular, for the 10 robot case, the computation time is reduced from about a week to about a minute. And here we use branch and play in a high fidelity drone simulation, where we want 6 drones to form a half circle around a leading drone, which has this black trajectory. And with branch and play, the drones can quickly form the desired pattern without colliding with each other. And here is the truck example you saw at the very beginning of my talk. They were actually coordinated by this branch and play algorithm. And you can see the trucks were dynamically swapping their ordering in order to maintain safety and optimize their group performance. And here's another example. In the end, you will see that these trucks were able to safely form a platoon around the outer loop, which is the highway in this mini city setup. Yes.
The number of communications is linear function of the number of agents here, but basically every follows their own corresponding leader.
Exactly. It's a chain communication graph.
Not everyone has to talk to each other.
No. That's one advantage. I guess you want to use this. Yeah.
But if they want to switch their follows or leads,
yeah,
I guess that's where you might need
you need exactly. You need to know who is your new leader, who is your new follower. Basically, you only need to know who is your new follower, because the leader has the responsibility to communicate its trajectory or plan to the leader, but not vice versa. But it's linear complexity, as you mentioned. Yeah, for sure. Okay. So one immediate question you might have here is, what if some of the trucks are driven by human drivers and they do not necessarily comply to the order of play that is dictated by the, let's say, AI regulator? So although we didn't cover this in our original paper, but we were happy to discover some concurrent work that exactly look at the problem. So the core idea is to form a belief state over the human's preferred order of play and have the robot actively adapt and so actively infer and adapt to it. So this is actually a perfect example that resonates with the key idea of my talk today, which is robots should strategically plan in the joint space of physical and information states to improve their safety and performance. And today we have seen that this exact same idea can allow robots to interact with people more safely and efficiently. And it not only provides verifiable safety assurances, but it's also practical for a lot of real-world robotics applications that is deployed on hardware systems. This from driving to racing and to locomotion. And the same game-theoretic principle can be applied to both cooperative and adversarial settings. And more broadly speaking, this idea has been followed and highlighted by a lot of research labs, companies, and government agencies across the globe. They have applied my approach not only to autonomous driving, but also to other application domains like navigating fixed-wing aircrafts and human swarm interactions. While these are all exciting progresses in human-centered robotics, I think there remain some very promising ideas that can allow us to make robots even safer and smarter around people. And now I want to share with you some of the future directions that I'm really excited about. So first and foremost, I think there are some exciting but rather underexplored connections between dynamic game theory and foundation models. So for all these game-based policies that we just saw today, their interactive behaviors are interpretable, which is nice. And we know how to add constraints in this game framework to capture things like vehicle dynamics and the hard safety requirements. But on the other hand, we have to be very careful about specifying the costs or rewards for these agents. And sometimes a handcrafted cost might give you the issue of reward hacking. For example, in a very complicated traffic intersection scenario like this one, how should we mathematically specify this nuanced objective, like passenger comfort, prediction of these many agents' future movement, and some cultural norms? For example, the driver behavior in New York City is somehow different from here in Baltimore. And finally, scaling can become an issue if you have too many agents or if you are using some ill-conditioned costs. On the other hand, we have seen some recent work that has looked into using a foundation model to make robots decision. And these models have been trained on massive data sets, and they can generate realistic trajectories that are also consistent with the scene. And once trained, they are inferenced, and they can generalize in new environments zero or few shots. And once trained, their inference time computation is very efficient and scalable. But if we are going to directly apply this method to robotic systems in real-world settings involving humans, then you might get crash, and yet another crash. Fundamentally, these models are ultimately black boxes, and we do not yet have a principled way to ensure or just verify their safety in closed loop. And it will be ideal if we can combine best from both worlds. For example, can we guide a safety-focused game policy with some data-driven prior knowledge offered by a foundation model? So here we have some early ideas based on that principle. So we have formulated a special kind of dynamic game, which we call KO game. The idea is that we are trying to align a game policy with some data-driven reference policy. And we do that by penalizing their KO divergence. And we have derived a closed-form solution that allows us to solve the game efficiently and be able to implement the controller in real time on hardware systems. So here we briefly tested this idea on the Waymo's WayMax simulator. The dynamic game here is defined to tackle things like safety specification, like not crashing with each other or not driving off the road. And again, we use the MTR model to produce a data-driven reference policy, which can closely mimic our day-to-day driving behavior. So on the right, if we directly use the MTR-based policy as a black box, you can see that the fast-moving car number 0 in the middle ended up colliding with the slow-moving car that is trying to pull out and merge into the traffic. On the left, with the KO game policy, we see that because of the additional safety incentive that we have in the game solver, the fast-moving car can slightly deviate to the left and avoid the slow-moving car that's trying to merge and into the traffic. So in general, I think based on this idea of blending games and data-driven prior knowledge, there's a really exciting line of research going ahead. And we'll be able to really scale up these interactive robot behaviors, make them generalizable across different domains, and more importantly, give them the necessary safety assurances that we care about. And this is especially useful for some safety critical shared autonomy setting like robot-assisted surgery. There, the robot might need to work closely with a human surgeon, and any single safety failure might mean catastrophic outcomes. And Axel and his students here have done amazing work at learning the control policies from these systems from human demonstrations. And now we have an opportunity to build on his work and also this idea of blending games and data-driven prior knowledge to further enhance the robustness and reliability of this kind of systems. So now that we are talking about shared autonomy, I want to say that in many of these settings, the human will be expected to make the majority of decisions independently by themselves. So the robot should be mindful of preserving that human agency. For example, when facing an emergency, a driver assistance system will first warn the driver with some audio or visual cues and only step in with physical interventions when a collision is imminent. So can we extend this human-centered design principle to design a formal safety filter that preserves human agency? And we want that design to be generally applicable not only to driving, but also to other shared autonomy settings like manufacturing, surgery, and robot-assisted feeding. And I argue that we can achieve that vision by building on this belief-based safety filter we have already seen today. Because that safety filter already allows the robot to reason about the people's internal states. And that is super useful for aligning the robot's decision with the human's decision. But I think there's still one missing piece here. That is, how should the robot account for how the human is trying to understand the robot? And this bi-level or bidirectional learning is important because in many cases, direct communication between human and robot is not practical. And the robot needs to find a way to message the human about what they should be expecting from the robot. And I think one way the robot can effectively steer the human's internal states is to provide multimodal interactions beyond just physical intervention. And this includes, for example, displaying some visual of safe sets to human using virtual reality devices, or providing some audio instructions to the human about the robot's next move, or some haptic feedback that warns the human of an upcoming emergency. So based on that idea, I have been collaborating with Toyota Research Institute to build an AI co-pilot system, and you have seen that in the earlier part of my talk. So here, if we only use a basic safety filter that completely overrides the human, it can produce some rather abrupt interventions that can actually confuse the human and cause them to lose their strategic edge and ended up spending extra time to recover to their normal racing pace. And in this example, you can see that this kind of human unaware safety filter can even prevent the human from successfully overtaking the opponent, even if in this case, the human could have completed that overtaking maneuver safely and successfully. And this is a prototype human-centered safety filter, which is designed to actively preserve the human agency. And it will try to respect the human decision as much as possible and help the human make that overtaking maneuver gently and smoothly. So today I have introduced several neural safety filters in order to compute safety filters for high-dimensional robotics tasks. And empirically, we have seen some promising robustness and scalability with these neural safety filter methods. But in practice, we haven't really talked too much about how should we verify the robot's safety assurances at runtime. And I think that is one of the most challenging but also rewarding open research question with robot safety nowadays. And in particular, I think there are two ways we can go about this. First, we can consider reachability analysis for dynamical systems enclosed with a neural safety filter. And I have done some early work on this with Makia. And now researchers have actually come up with much more efficient and scalable algorithms for doing this. And it is an exciting time to go back and think about combining this approach with some of the emerging robot learning algorithms. And the other opportunity is to use statistical methods like conformal prediction or scenario optimization so that we can validate the safety filter and provide high probability safety assurances. So I hope throughout this talk, I have painted a picture of what I think next generation human-centered robotics might look like. And this kind of system must be scalable and trustworthy. That means verifiable safety and performance assurances. And I think we are really at an exciting time of being able to connect all the dots here and build robots that we can really trust. And I know that many researchers here at JFU share the same vision, and I just can't wait to collaborate with you and push these boundaries together. So with that, I want to thank all of my collaborators from Princeton, CMU, Toyota, and Honda, who really made all these results I present to you today possible. And thank you very much for listening, and I look forward to your questions.
Here.
In the second part of your talk there, you were talking about the particular
Reinforcement learning.
Yeah. So you have the scenario where you have every agent is can be both leader and both follow. So you're kind of distributing the load of leadership in your population. The alternative scenario is where the leader is centralized. You have one single leader that kind of orchestrates the whole thing. That also has linear communication because everyone only talks to a single leader. But I'm wondering why you choose this kind of distributed follow leader paradigm over that centralized coordination.
Just to make sure you are talking about the third one actually for the truck, right?
Oh yes.
Yeah. So absolutely, you're actually right. So that approach is actually a mix of centralized and distributed communication. So there is actually a centralized part, which is the communication between the regulator and the agents. So the regulator need to broadcast the ordering to the agents. So that part is centralized communication, but that is extremely, let's say, efficient because it, in practice, it only needs to broadcast a number. So what's your ordering? And probably some headers because the regulator needs to let each agent know who is your follower and who is your leader.
So that decision is done in a central, by a centralized regulator.
Exactly. So the optimization for the optimal ordering is done by, let's say, a centralized agent. And once that upper layer optimization is done, you will have a list of orderings, and then that regulator needs to broadcast that orderings to each individual agents. And then,
the decision of when to change the ordering is also done by the regulator.
Exactly. Think about like air traffic control. I think it's the same way that it's done in air traffic control, because the air traffic controller is the regulator, and it kind of decides which airplane lands first, which one will do some evasive maneuver to give way to other aircrafts. Yeah, for sure.
I have one more question, but I'm going to let other people.
Yeah. So.
Great talk. Thank you so much. A little bit curious about the application of your work in potentially surgery now. So there, it's very hard to define kind of safety, right? Because you in autonomous driving, you can define kind of collision, like getting too close to another vehicle. In surgery, we have to get close. We do cutting, cautery, all these things, right? So any idea, how some of your ideas would apply there?
Yeah, so actually there's a big push in the robot safety community right now to actually move beyond like traditionally, let's say handcrafted safe sets. Like in autonomous driving, it's clear that if cars don't crash, if cars don't drive off the road, you are safe. As you mentioned in robot surgery or in other like for example, smart manufacturing settings, the environment is super complicated and it varies case by case. And it's very hard to define, geometrically what are the safe sets, what are the failure sets. So the push is we are moving from, some Euclidean space to some latent space. So you'll be able to compute the safety filter using the same exploitability formulation I presented today, but apply that in some latent space, which kind of implicitly captures the safety specification. Of course, the challenge there is how do you actually verify that once you move away from latent space to the actual physical space in reality, the kind of safety guarantee still holds. It's pretty much an open research question. But yeah, as you mentioned, I think the first step, I think it's promising is to do this latent space reasoning and potentially using some like a world model, which at least allow you to do one step forward, like collision checking, to at least raise a flag of whether there might be some safety issues. And if there is some safety violations, at least you can like move the control from the robot to the human and to make sure things stay safe. But again, if we want to move to like purely autonomous robot surgery with safety guarantees, I think, yeah, that's a million dollar question to me. Yeah.
All right, any other questions? Yes, yeah.
Yeah, I was going to ask about this ODD that you called it. I mean, that's essentially, I guess, you're trying to put some boundaries on, for example, how fast a human can move. Is it
Right.
that level of specification?
Mhm.
Okay.
Yeah.
I mean, that can vary a lot, right? And if I'm driving and I see somebody walking on crutches on the side of the road, I probably don't expect them to run across the street in front of me.
Yeah.
But so is there some complexity that you do to not have to assume sort of an Olympics sprinting performance for everybody you see on the side of the street?
Yeah, absolutely. So let's imagine if that kind of situation you just mentioned is happening on a highway, then think about a robot that has an ODD of covering that edge case on a highway. Then probably you will see that robot will never move on a highway, and you will never want to use that kind of autonomous vehicles, right? So I think maybe one of the work that can help address that issue is the belief space safety filter I talked about, because that theta, that sort of information variable can actually, you can use that to represent the different environments, like whether the robot is driving on a highway where it is unlikely that a human is trying to suddenly jump into the highway and jam the robot, or if you are driving in like a very busy urban scenario where the safe strategy might be very different.
It's like perception, perception the robot has of the environment.
Yeah, exactly. Yeah. But yeah, I guess the ultimate goal we want is for these safety filters to be adaptive to the changing environment. And but again, as you said, I think to me it's beyond an engineering problem. I think engineers need to actually work with policymakers to really, flesh out what are the necessary ODD for example, these autonomous driving examples. As you mentioned, for highway driving, the ODD could be very different from like urban driving. So I guess policymakers need to work with engineers to make sure that this ODD makes sense. And given this ODD, our robot safety engineers can come up with safety assurances. Yeah. Oh, 2 questions. Maybe you can go first.
Great talk.
Thank you.
I'm very curious about like the agentic things in the robotics, because nowadays we have a new trending of the embodied intelligence. Yes, and a lot of robotics are controlled by the language model, like the language model driven agents.
Absolutely.
And we are also using the reinforcement learning to train a model to make decisions and using tools. So what do you think of the relationship between the traditional reinforcement learning based robotic control system and the new coming language model driven agent system? And is there any opportunity to combine these two technologies together to solving the real world challenge?
Yeah, that's a fantastic question, and also a fantastic comment, I would say. And definitely, I think now we are at an exciting time where a lot of different techniques from different communities are merging together to really build robots that are intelligent. And I would say that fundamentally, whether you're using like trajectory level, motion planner, or you're using an LLM to make a robot decision, the robot is making decisions. And it makes sense to me that you're using RL to train this decision-making module for either low-level robot motion planning or control or high-level sort of semantic level reasoning for the robots. And to me, I think at this point, it makes sense to use an LLM at a higher level. And that is especially useful for reasoning safety in an unstructured environment. For example, we can use LLM or BLM in particular. Like you can input some prompt that comes from the user, and also you input the current image of your environment, and let the robot reason what are the unsafe sets in the environment. And then below that, we have these traditional safe control methods, or not traditional, like RL-based safe control method that I've been focused on. We can use that to reason trajectory level robot safety. So I think the combination of higher level LLM reasoning and lower level trajectory level execution of safe robot control policy is definitely a promising future direction. Yeah.
Thank you. We worked out these and it's really excellent. I was wondering, like, because you mentioned about the deep scenario, so like through the test policy and also the dynamics model and learning scenario, how do we envision like integrating some like reachability analysis, like with the Jacobi, which kind of do optimize upon the zone dynamic models, like the consumer prediction.
So let me try to repeat your question is how, so you're wondering how should we combine this deep reinforcement learning approach with Hamilton-Jacobi reachability?
And probably with conformal prediction, which kind of.
Yeah. Yeah, so I think there's already like a natural connection between these, let's say, different methods. For example, the connection between reinforcement learning and Hamilton-Jacobi reachability is that for Hamilton-Jacobi reachability, if you want to solve the robot policy, you need to solve that Bellman equation, Hamilton-Jacobi Isaacs equation. And also, on the other hand, reinforcement learning is essentially approximate dynamic programming. So what you can do is you can add a discount factor to the HJ Bellman equation and turn that into a reinforcement learning problem. And that's exactly what I did in the adversarial, basically in the second part of my talk today. So that same sort of actual predictive reinforcement learning paradigm can be used to approximately solve the two-player HJ reachability problem. But now the remaining challenge is after you get a neural approximated HJ value function, how would you verify that which part of the state space does your recursive safety guarantees hold, and which part doesn't have these safety guarantees. And that's where conformal prediction can come into play. And there are some recent work, not by me, but by some folks at USC and Stanford, where they show that you can use conformal prediction, you can apply it in the simulator to exhaustively test your HJ value function on different places in your safe space, and then you can get a sort of, I guess, lower bound on the safe rate when you are deploying that system in the real world setting. So I think that's where conformal prediction is a useful tool to give some guarantees. Yeah.
Okay. We are out of time, so let's thank the speaker again.